A read replica and a multi-AZ standby both give you a second copy of your database. One fails over automatically when the primary dies. The other leaves your team hand promoting a replica for 47 minutes while the site is down. Two options that both look reasonable, and one word in the requirement that quietly picks the winner. Stack Lessons, Episode 37, Answer Incoming. By the end of this video, you'll be able to walk into 10 of the most common architecture forks and pick the right branch on judgment, not luck. This is the synthesis episode. We've built all the pieces across this course, and now we assemble them into the decisions that separate an engineer who knows the services from an engineer who knows the architecture. Over the last 30-some episodes, you've learned the individual services. In episode 18, we covered multi-AZ and read replicas. In episode 6, fetching secrets at runtime. In episode 10, gateway endpoints. In episode 19, disaster recovery tiers. Now we stop looking at them one at a time and start making the calls a senior architect makes daily. And here's the payoff. Every one of these 10 decisions traces straight back to a well-architected pillar you already know. Here's the thesis for the whole episode. Passing the exam and building systems that survive production are not two different skills. They're the same skills seen from two angles, both rooted in the same engineering principles. Megacorp has real scars from every one of these decisions, so we'll walk each one as a production story first, and the exam payoff falls out naturally. Before we start, here's the map. The well-architected framework has 6 pillars, and every decision in this episode lands on at least one of them. Reliability owns the most ground. That's failover, deployment safety, statelessness, decoupling, and disaster recovery. Security covers credentials, private network paths, and encryption. Cost optimization covers network paths again, tier selection, and right sizing. Performance efficiency and operational excellence each pick up a couple, and sustainability runs quietly underneath all the right sizing work. The habit to build is this. Read the requirement, name the pillar it's testing, and let that narrow your answer. Minimize downtime means reliability. Protect data means security. Reduce cost means cost. Scale automatically means performance. Decision 1. Megacorp's primary RES instance fails right at peak traffic. The good news, they thought, was that read replicas were already running for reporting queries. Surely those provide high availability, right? So the team starts the failover, except there's no automatic failover. They spend 47 minutes manually promoting a replica, rewriting connection strings, and restarting app servers, all while the site is dark. The infrastructure they trusted for availability was never built for it. The mistake sits in one sentence. I have 2 database instances, so I have high availability. It feels obviously true, but having a second copy of your data is not the same as having automatic recovery. The question is whether that second instance can take over on its own, or whether a human has to step in. That single distinction is the whole decision. Here's the mental picture. Multi-AZ is a hospital's backup generator. It exists for one job, keeping the lights on when primary power fails. Its replication is synchronous, so there's 0 data loss, failover is automatic, and the DNS endpoint never changes. Day to day, that standby serves no traffic at all. Read replicas are extra checkout lanes at a grocery store. They handle more throughput, but their replication is asynchronous, so they can lag seconds behind. Promotion is manual and produces a new endpoint. And if the store manager walks out, a checkout lane cannot suddenly start managing the store. So the rule is clean. When the requirement says failover, high availability, or minimize downtime, the answer is multi-AZ. When it says read heavy, read scaling, reduce load on the primary, or reporting queries, The answer is read replicas. These two are never interchangeable, and the word in the scenario tells you which one you're being asked for. There's one option that does both, and it's worth knowing. The 2-standby multi-AZ DB cluster gives you automatic failover in under 35 seconds and 2 readable standbys at the same time. The classic single standby multi-AZ instance cannot serve reads at all. That standby is idle until it's needed. This whole decision maps to the reliability pillar. Best practice rel 10 BP01, deploy your workload to multiple locations. Decision 2. A megacorp developer needed an application on EC2 to call Amazon Web Services, and setting up a role felt like a hassle. So they generated access keys and pasted them into a config file. That file went into version control. A month later, the repository was made public during a migration. Bots that scan public repos for credentials found those keys within minutes and spun up hundreds of mining instances across multiple regions before anyone noticed. Amazon Web Services doesn't call this a bad habit. They call it an anti-pattern in the well-architected framework itself. The guidance reads, a common anti-pattern is embedding IAM access keys inside source code, configuration files, or mobile apps. When a key is required to talk to an Amazon Web Services service, use temporary security credentials instead. Long-term keys persist until someone manually rotates them, and they can leak anywhere: logs, config files, commit history, with no alarm. The right pattern has two halves, and Megacorp fixed both back in episode 6. For Amazon Web Services API calls, attach an IAM role to the instance through an instance profile. The instance metadata service delivers temporary credentials that STS rotates automatically. They're never in source code, never in a config file. That's the replace step. For third-party credentials like a database password, the app calls Secrets Manager at runtime through the SDK, caches the response, and stores nothing. That's the rotate step, encrypted at rest, rotated on a schedule, fully audited. The rule to carry: an IAM role for anything calling Amazon Web Services APIs, and Secrets Manager fetched at runtime for third-party credentials. 0 static keys anywhere, not in user data, not in environment variable, not in an AMI. On a scenario, any answer that embeds a key in a fixed location is the wrong answer. This is the security pillar. Best practice SAA-C02 BP03. Decision 3. Megacorp's procurement servers stored in private subnets and read and write S3 and DynamoDB constantly. To reach them, that traffic was routed through a NAT gateway, which charges about 4.5 cents per gigabyte it processes. And here's the thing nobody questioned: that data never actually leaves Amazon Web Services. It's going from EC2 to S3, both inside the same account, but the bill climbed every single month anyway. Look at the same traffic down 2 paths. 10 terabytes a month to S3 through a NAT gateway runs about $450 in processing charges. The exact same 10 terabytes through a gateway endpoint costs $0. Not discounted, $0. No hourly fee, no per gigabyte charge. The destination didn't change, only the path did. Routing S3 traffic through a NAT gateway is like paying a toll to drive on a private road inside a gated community, when both the source and the destination are already inside the property. The gateway endpoint is the free internal road that was always there. So the rule: S3 or DynamoDB from a private subnet, reach for a gateway endpoint. This is one of the highest return, lowest effort changes in all of Amazon Web Services networking. One configuration detail decides whether it works. The endpoint only takes effect once it's associated with the right route tables. Miss that association, and traffic silently keeps flowing through NAT as if nothing changed. This choice is a security win as well, because it keeps that traffic off the public internet entirely. And to keep it distinct from episode 10, interface endpoints reach over 100 other services, but they bill per hour and per gigabyte. Gateway endpoints for S3 and DynamoDB only are free. 3 down, and a pattern is already forming. Availability is a different dial than read scaling. Temporary credentials beat static keys every time. And you don't pay NAT rates for traffic that never leaves Amazon Web Services. Notice what ties them together. In each case, the right answer was the cheapest, safest option that still met every stated requirement. That's the whole discipline in miniature. Decision 4 brings us to that 47-minute outage. Megacorp deployed a new order service at 10 at night with an in-place rolling update, new code replacing the running instances directly. A configuration error slipped through that only surfaced under real production traffic. And because the deployment had replaced the old instances, rolling back meant redeploying the previous version from scratch. 47 minutes of downtime, and nobody was watching closely enough to catch it early. Think of it as a railroad switch. An in-place deployment tries to replace the rails under a moving train. If something goes wrong mid-swap, there's no fast way back. Blue-green lays a second complete track alongside the first. The train keeps running on blue while you bring green up. If green has a problem, you flip the switch back in seconds. You never stop the train to rebuild the rails beneath it. Here's the wiring. An application load balancer listener points at 2 target groups, blue and green. Code deploy manages the traffic weight between them. When green deploys, code deploy waits for its health checks, then shifts a canary slice, say 10% for 10 minutes, before going to 100. And this is the piece that makes it self-healing. A CloudWatch alarm on the 500 error rate or latency is attached to the deployment group. If that alarm fires during the shift window, code deploy automatically shifts the listener back to blue. Blue never went away, so rollback is a pointer flip, not a rebuild. Now replay Megacorp's outage with this in place. The bad config surfaces during the canary window. Within 8 minutes, the CloudWatch alarm trips, and code deploy shifts traffic back to blue on its own. Total impact, 8 minutes of errors affecting only 10% of traffic, with no human awake to catch it. The 47-minute outage collapses into a rounding error. This decision lands on both operational excellence and reliability. Make frequent reversible changes and let the system heal itself. Decision 5 is about the tier you reach for versus the tier you need. Megacorp ran a nightly batch job on on-demand M5.2x large instances. The job tolerates interruption. If a node dies, it just reruns that chunk. It doesn't need guaranteed uptime at all, but on-demand was the familiar choice. So that's what they picked. For interruption-tolerant work, on-demand is the maximum price you can pay, and you get nothing extra for it. Amazon Web Services defines the goal precisely. The cost optimization pillar includes the ability to run systems to deliver business value at the lowest price point. Read that carefully. Lowest price point that still delivers the business value. Not the absolute cheapest thing available, and not the safest, most padded option just in case. The cheapest choice that satisfies every stated requirement. So the engineering judgment is reading each constraint in the scenario, the SLA, the latency target, whether it tolerates interruption, the durability need, and then picking the least expensive option that meets all of them. When 2 answers both satisfy the requirements and one costs less, the cheaper one is correct. The failure mode is choosing a higher tier just in case, which the framework calls designing by haste rather than by data. There are 5 levers that do the heavy lifting. Right size to your actual measured load. Commit the steady state baseline to savings plans or reserved instances. The third lever is spot. Run interruption-tolerant work there for work that was interruptible all along. The fourth is lifecycle policies. Apply them to data that cools over time and eliminate idle resources while you're at it. Teams that pull all 5 of those levers together typically report savings of 30 to 60% versus all on demand. Decision 6. Megacorp's SaaS app stored each user's session in the local memory of whatever instance they'd landed on. To keep users on that instance, they turned on sticky sessions. It worked fine in testing. Then autoscaling did its job during a quiet period and terminated an instance to save money, and every user pinned to that box was logged out at the same instant. Worse, new instances during a spike sat idle while the old ones stayed overloaded, because existing users were glued to their original server. Amazon Web Services is direct about this being a requirement, not a nice to have. The framework says systems should either not require state or should offload state so that between client requests, there's no dependence on data stored locally on disk or in memory. And then the key line, this allows servers to be replaced at will without causing an availability impact. Replaced at will. That's the entire promise of elasticity, and local session state quietly breaks it. A stateful app tier is like a restaurant where each waiter memorizes your order in their head. If your waiter is replaced mid-meal, the new one has no idea what you ordered. Sticky sessions just try to keep the same waiter assigned to you. They hide the symptom without fixing it. Autoscaling can't terminate freely, load runs uneven, and any instance failure loses sessions. The fix is a shared notepad at the host stand. Externalize session state to Elasticache or DynamoDB, and any instance can serve any request. Autoscaling adds and removes at will, and a failed instance loses no sessions at all. So here's a rule worth memorizing. Sticky sessions are never the correct answer to a scaling or elasticity question. They're the wrong fix for the right problem. When the scenario is about scaling a stateful app tier, the answer is externalizing session state, Elasticache Redis for sub-millisecond reads and rich structures, or DynamoDB for a simpler managed store with built-in expiry. This one touches both reliability and performance efficiency. Decision 7. Megacorp's order service called 3 downstream services directly and synchronously: fulfillment, notification, and analytics. Each order waited for all 3 to answer before it could complete. Then the analytics service hit a slow patch. And because everything was wired together in one synchronous chain, order throughput degraded right alongside it. The slowest link was suddenly setting the pace for the entire system, even though analytics is the least critical of the 3. The fix is the fan-out pattern. The order service publishes one event to an SNS topic and moves on immediately. SNS delivers a copy to a separate SQ for each consumer, one for fulfillment, one for notification, one for analytics. Each queue is a durable buffer. If the analytics consumer slows down, its messages simply pile up safely in its own queue while orders keep flowing and the other 2 consumers are untouched. And each consumer scales independently on its own backlog. Adding a 4th consumer later is just a new queue subscription, not a code change to the producer. So why not just scale each consumer on raw queue depth? The guidance here is clear. The number of messages in the queue might not change proportionally to the size of the fleet processing them. A queue of 1,000 quick messages needs a very different fleet than 1,000 slow ones. Raw depth ignores how long each message takes to process. The metric that actually tracks the work is backlog per instance. A few details separate a fragile fan-out from a hardened one. Scale on backlog per instance, messages divided by in-service instances, computed with CloudWatch metric math. Attach a dead letter queue to every queue, and set the max receive count to 3, not the default of 10. Then alarm on that dead letter queue's depth separately, A growing dead letter queue is your signal that a specific class of message has a bug. Finally, use SQS standard with idempotent consumers unless strict ordering is genuinely required. This decision serves reliability and performance efficiency both. 7 down, and one thread runs through all of them. Deployment safety, tier discipline, statelessness, decoupling. Every single fix makes the system more replaceable, more reversible, and more independently scalable. 3 decisions remain to close out the cost and resilience story: disaster recovery, encryption enforcement, and right-sizing. That's not a coincidence. It's what a well-architected system looks like. Decision 8. A team ran their production RDS database in a single availability zone, framing it as a cost saving. Then Amazon Web Services did routine maintenance for OS patching, and the instance was unavailable for about 15 minutes. 15 minutes of production downtime for a scheduled maintenance window? With multi-AZ configured, that same window triggers a failover to the standby in roughly 60 seconds. The outage cost them customer credits and an SLA breach, far more than the monthly cost of the second zone. We covered these 4 strategies in depth in episode 19, so here's the decision view. Backup and restore sits at the low-cost end, recovery in hours, appropriate for dev and test. Pilot Lite keeps your data replicated with compute switched off, recovering in tens of minutes. Warm Standby runs a scaled-down copy that's always on, recovering in minutes. And Multi-Site Active runs full production in multiple regions at once, with near-zero recovery time and the highest cost. The whole thing is a spectrum trading cost against recovery speed. And that red bar at the bottom is the line that matters. Single AZ is not a point on this spectrum. It's a single point of failure. One thing that's easy to skip, Amazon Web Services puts it plainly. It is critical to regularly assess and test your disaster recovery strategy so you have confidence in invoking it when you need it. A DR plan that has never been exercised is not a plan, it's a hope. Amazon Web Services even recommends using Reboot with failover in non-production to prove your application reconnects and your DNS time to live is set correctly before the real outage forces the question. The rule is to treat DR like insurance. You don't buy maximum coverage for a garden shed, and you don't insure a data center with a policy that pays out in 24 hours. Map the business's actual recovery time objective and recovery point objective to the cheapest tier that satisfies both. Don't default to active out of fear, and never leave production in a single zone. Decision 9. Megacorp configured default server-side encryption with KMS on a bucket, with the customer-managed key their compliance team required. Job done, they figured, but the audit came back and found objects encrypted with the wrong key. Here's why. Default bucket encryption only governs uploads that arrive with no encryption header at all. If an upload explicitly asks for server-side encryption with S3 managed keys, or names a different key, that request slips right past the default and is honored as written. The default is a fallback, not a fence. To actually enforce the key, you need a bucket policy that denies the upload. Amazon Web Services documents the exact pattern. To require server-side encryption of all objects in a bucket, use a bucket policy that denies put object to everyone when the request does not include the header requesting the specific SAA-C03 key. That deny statement is the bouncer at the door. The default encryption setting is just the sign on the wall, helpful, but it stops no one. This is the statement that does it. The effect is deny on the put object action for the contracts bucket. The clever part is the condition. It checks whether the KMS key ID header is null. In other words, whether the request failed to specify the required key. When that header is missing, the null check is true and the upload is denied outright. Any object that lands in the bucket had to name the correct key to get there. This is exactly the policy Megacorp adopted back in episode 7. The full stack is 4 layers: SAA-C03 with a customer-managed key, so every encrypt and decrypt shows up in CloudTrail for audit. The deny unencrypted puts policy, which closes the gap between what's configured and what actually landed. Block public access on at both the account and bucket level. And one cost detail that matters at scale: enable S3 bucket keys, because without them, every object put and get triggers a separate KMS call. Amazon Web Services says enabling them cuts those KMS request costs by up to 99%. One more constraint that shows up constantly in cross-account scenarios. Amazon Web Services states it directly. Objects encrypted with an Amazon Web Services managed key cannot be shared cross-account. If you need another account to read your encrypted S3 data, you must use a customer-managed key whose key policy grants that access. Amazon Web Services managed keys are scoped to your account and simply cannot cross the boundary. This whole decision lives on the security pillar, best practice SEC-08 BPO2, enforce encryption at rest. Decision 10, the last one. A team running 500 on-demand instances wanted to cut costs, so they committed to 3-year standard reserved instances across the fleet. Smart move on the surface, up to 75% off, but 6 months later they finally turned on Compute Optimizer, and it showed that 40% of those instances were running under 20% CPU. Badly over-provisioned. And standard reserved instances cannot be canceled. They'd locked in the wrong baseline for nearly 3 years. Committing to reserved instances before right-sizing is like signing a 3-year lease on an apartment before you've decided how many rooms you actually need. The order is backwards. Compute Optimizer is the step where you measure how many rooms you use before you sign anything. Get that order wrong, and you don't just overpay once, you lock the overpayment in for the full term with no refund. Here's the correct sequence. First, install the CloudWatch agent. Without it, recommendations have no memory data, and memory is the constraint that most often binds. Second, let Compute Optimizer measure your real production load, 14 days by default, up to 93 with enhanced infrastructure metrics. Third, right size to your actual 99th percentile usage. Fourth, commit that stable, right size baseline to savings plans or reserved instance. Fifth, run the interruptible remainder on spot, backed by SQS retry so an interruption just returns the message to the queue. Measure, then commit, never the reverse. Once you're ready to commit, know your options. Savings plans commit dollars per hour rather than locking to a specific instance. The Compute Savings Plan is the most flexible, up to 66% off, applying across EC2, Lambda, and Fargate. The EC2 Instance Savings Plan goes deeper at up to 72%, but locks you to one instance family and region. Neither one reserves actual capacity, they are discount rates only. Reserved instances work differently. A standard RI reaches up to 75% off, but cannot be exchanged once purchased. A convertible RI gives you a significant discount and can be swapped for a different instance type. And a zonal RI is the one option that also reserves actual launch capacity in a specific availability zone. Here's the whole episode on one board. Reliability owns decisions 1, 4, 6, 7, and 8, failover, safe deploys, statelessness, decoupling, and disaster recovery. Security owns 2, 3, and 9, credentials, private paths, and encryption. Cost optimization owns 3, 5, and 10. Performance efficiency picks up 6 and 7 again, and operational excellence claims decision 4. Look at how a couple of decisions serve 2 pillars at once, because good architecture rarely optimizes just one thing. And the one habit underneath all 10, read the requirement, name the pillar it's testing, then pick the cheapest option that satisfies all of it. The same principles that pass the exam are the ones that survive production. Carry these forward. Failover means multi-AZ, read scaling means replicas, and the two are never interchangeable. No static keys ever, roles for Amazon Web Services calls, secrets manager at runtime for the rest. Free gateway endpoints for S3 and DynamoDB, and blue-green deploys gated by a CloudWatch alarm so rollback is automatic. Externalize session state and decouple with SNS and SQS scaling on backlog per instance. Match disaster recovery to the real recovery objectives. Enforce encryption with a deny policy rather than trusting the default. And always right size before you commit. Now let's see how well all of this landed with a quick 5-question quiz. Question 1. A company runs a production RDS database with a read replica handling reporting queries. When the primary fails at peak traffic, the app is down for 47 minutes, while engineers manually promote the replica and rewrite connection strings. Which change would have given them automatic recovery with an unchanged endpoint? Option A, add a second read replica in a different availability zone. Option B, reconfigure the deployment as multi-AZ with a synchronous standby. Option C, increase the replica's instance size to speed up promotion. Or option D, enable more frequent automated snapshots. Run the failover versus read scaling rule before you answer. The right call here is B. Multi-AZ keeps a synchronous standby that fails over automatically, and the DNS endpoint never changes, so no application reconfiguration is needed. Read replicas, no matter how many or how large, use asynchronous replication and require manual promotion to a new endpoint. That's read scaling, not availability. Question 2. An application on EC2 needs to call the S3 a PI, and it also needs a third-party database password at startup. Which approach follows the Amazon Web Services recommended pattern with 0 static credentials? Option A, store both the Amazon Web Services keys and the database password in the EC2 user data script. Option B, embed the Amazon Web Services keys in the AMI and fetch the database password from parameter store as plain text. Option C, attach an IAM instance profile for S3 and fetch the database password from secrets manager at runtime. Or option D, hard code temporary credentials in an environment variable and rotate them weekly. Pause here if you want more time. This one is C. The instance profile delivers temporary auto-rotated credentials through the metadata service, so no Amazon Web Services keys ever touch your code. The third-party database password belongs in Secrets Manager, fetched at runtime, encrypted, rotated, and audited. Every other option leaves a static credential sitting somewhere an attacker can reach. Question 3. EC2 instances in a private subnet transfer roughly 10 terabytes a month to S3, all routed through a NAT gateway, and that traffic never reaches the public internet. What's the most cost-effective change? Option A, add a VPC gateway endpoint for S3 and associate it with a private subnet route tables. Option B, replace the NAT gateway with a smaller NAT instance to lower the hourly rate. Option C, add an interface endpoint for S3 over private link. Or option D, move the instances to a public subnet to bypass NAT entirely. Lock in your answer before I give it away. The answer is A. A gateway endpoint for S3 is completely free, no hourly charge and no per gigabyte processing fee, and it routes traffic over the Amazon Web Services backbone. Just remember to associate it with the right route tables or nothing changes. An interface endpoint would still bill per hour and per gigabyte, and moving to a public subnet throws away your security posture to fix a cost problem. Question 4. A SaaS application stores session data in each instance's local memory and uses sticky sessions on the load balancer. During scale-in, thousands of users get logged out at once, and load is uneven. What's the correct fix? Option A, disable auto-scaling so instances are never terminated. Option B, increase the sticky session duration so users stay pinned longer. Option C, add more instances and let the load balancer rebalance existing sessions. Or option D, externalize session state to Elasticache or DynamoDB and disable sticky sessions. Think about which constraint matters most here. If you said D, well done. Sticky sessions only mask a stateful app tier. They never fix it, and every alternative here just doubles down on the workaround. Once you externalize session state to a shared store, any instance can serve any request. Auto-scaling terminates and launches freely, and an instance failure costs 0 sessions. That's the reliability best practice, L005, BP06, in action. Question 5, the last one. A team commits to 3-year standard reserved instances across 500 on-demand servers. 6 months later, Compute Optimizer shows 40% of the fleet running below 20% CPU. What sequencing would have avoided locking in that waste? Option A, right-size using Compute Optimizer first, then commit the stable baseline to savings plans or ARAs. Option B, commit to convertible R, is instead and exchange them repeatedly as usage drops. Option C, buy savings plans up front since they can be canceled anytime. Or option D, move the entire fleet to Spot to eliminate commitment risk. Got your pick? Let's see. It has to be A, and here's why. The correct order is always measure, then commit, install the CloudWatch agent, let Compute Optimizer analyze real production load, right size to actual usage, and only then commit the stable baseline. Like standard R is, savings plans carry a fixed commitment with no cancellation option, so option C is simply false. And Spot can't carry a fleet's steady-state critical work. Sign the lease after you've counted the rooms, never before. And that closes production patterns. 10 Amazon Web Services architecture decisions senior engineers get right. Subscribe so the rest of the Cloud Architect path reaches you automatically and gets in front of new learners. Tell me what helped and what was still fuzzy. I read every comment. Got a certification on your list I should cover? Suggest it below. And honest feedback on the style or pace is always welcome. See you in the next lesson.